is a very special kind of motion. That first of all, uniform means that the speed of the particle or the object is a constant. However, because it's circular motion, the velocity is not constant. Velocity is a vector. It has direction and magnitude. Therefore, imagine that we have a particle of P. It has a distance r away from the origin. If this particle keeps the same distance from the origin and start to travel a circle, well, the character of circular motion is obviously this object P is always the same distance away from the origin. That is the radius of the circle. Now, in order to be uniform, that it has to turn the same amount of angle within the same amount of time, we use a physical quantity called omega to define. Omega is the change of the angle over time, and we give a name called angular velocity. The reason it is velocity, that is because omega in this case is counterclockwise. We could have this particle P to rotate clockwise. So therefore, if we have a choice of direction, either clockwise or counterclockwise, then this is a velocity because it has direction involved. And the unit for omega is the unit of angle over time. In the SI unit, the time is in second. Angle is basically dimensionless. However, in order to indicating this is an angle, we create a unit for the angle. It's called radian. So it is radian over time, which is second. It's radian over second. Now let's think about this unit of radian. We have learned before that if we have a circle and then we have radius, the relationship of radius and an angle theta and the arc corresponding to this angle theta is L equals to R times theta. And also we know that the formula for circumference, that C is for circumference equals to 2 pi of R. So if we compare this equation and equation of circumference, we realize that both are of radius, and this L is the arc corresponding to the particular angle theta, and then this 2 pi is the angle for one revolution corresponding to the arc of a circle, entire circle circumference. Therefore, we use 2 pi to present the angle for one revolution. That 2 pi has a unit of radian. On the other hand, we said one revolution equals to 360 degrees. This is an arbitrary number because we choose 360 degrees. It can be evenly divided by many numbers, for example 3, 5, 6, and so far so forth. Therefore, if we want to get an angle between the degree and radian, we can easily say if theta is in degree, we want to get in radian. So this is theta in degree and this is theta in radian. They should be proportional. So for example, that pi radian is 180 degrees, and we can make this equal. What does that mean? For example, if we know the angle is 21 degrees, we want to get 21 degrees into radian. What we do, we just plug in the value of that 21 degrees right here, because we say 21 degrees, we want to know how much radian. And then we said 180 degrees is this much radian, is pi radian. So it should be proportional. This is an equation that we can convert from degree to radian. All right, let's come back to this uniform circular motion. Now, in order to be uniform, the speed has to be a constant. So what happened is, if we travel around the circle, if we spend the same amount of time for L, then the speed is a constant. So let's look at this. L equals to r theta. If we differentiate, we have dl dt equals to r is a constant, that's radius, and d theta dt. So the dt is v, how fast we travel around a circle, and the theta dt we just define as delta theta over delta t. We define that as omega. So that the theta dt is the instantaneous omega. This tells us if we keep an omega as a constant, then v will be constant. So when we have uniform circular motion, v is constant and omega is constant, so both are constant, and both are related in the equation that v equal to r omega. So we say tangential v, tangential speed, equals to radius times angular speed. We're talking about magnitude, but obviously both we have a name, omega as angular velocity and v as tangential velocity. So now if omega is in radian per second, then omega times t will give us an angle, it turned in t second. So the angle here is counterclockwise, that equals to omega times t. So anytime this position, the position of particle p, can be expressed as, since the distance is r away from the origin, this is always origin, so the position can be the OP, always say the particle p's position, the OP vector can be expressed as r of cosine omega t of I plus r of sine of omega t of j. That is the position of particle p. Always say that is the vector of OP's expression. It has x component and has y component. Now let's take a look at what happened from the graphic point of view before we go into the detail of mathematics. That a circular motion, take a look at it here, and a particle travel around a circle. So imagine this is actually we can look at this B, this is amplified picture. Initially we have the particle at location A, and the velocity v initial is this much. And delta t second later, the particle is at location B, and let's name the velocity is v final. Now I want to point out that the lengths of v initial, v final are the same, because remember, for the vector, the lengths represent the magnitude. Since this is a uniform circular motion, which means the v initial magnitude should equals to v final of magnitude at any time. So the lengths of the vector are the same. Now, since this is initial, r initial position vector, this is r final, so the change delta r is from A point to B, because A is initial position, B is final position. And we know that our r final minus r of initial give us delta r. Okay, so if we construct a velocity vectors addition, because what happened is we have this change of velocity issue in this case. Even though the magnitude of v initial, v final are equal, but the directions not. Look at it, v initial is pointing that way, v final is pointing down, because circular motion requires change of direction. Otherwise we cannot come back to finish one circle. So this tells us as a vector, when the magnitude even is a constant but direction changes, there is a change of velocity. It defines a change of velocity as v of final minus v of initial. We learned a vector minus another one actually is a vector plus that of a negative one. This is the same. So minus v initial is plus a negative v initial. So look at this, that our v final is pointing this way, right? If we take a look, this is v final. Our v initial is this way, but we want to have a negative v initial. How do we do that? Well, it's very easy. It's just simply need to make opposite direction and same magnitude. So this opposite direction will be that way and same magnitude. So our negative v initial is that way compared to this v initial. Now we want to add v final and negative v initial. So how do we add them? Well, we learned we just use this vector and the other vector to construct a parallelogram. So the parallelogram is like that, and the resultant is the diagonal of this parallelogram. So who is the resultant? The v final plus a negative v initial, the resultant is delta v. So delta v is this guy. Now, I simply follow that when a vector are parallel to each other, well, this v final represent that v. V initial is this way, that our negative v initial is the opposite way. So actually what I'm doing is, from this picture, I'm working on this picture. The particle initially is here, final is there. So delta v, it looks like point to the center of the circle. And we give this direction special name called centripetal. Centripetal means point to the center of the circle. So there's something very interesting. We learned that average acceleration is change of velocity over time. So right now, if our change of velocity delta v is centripetal, and then our average acceleration will be centripetal because delta t is a scalar. This is very true that our acceleration is centripetal during the circular motion. So usually we will use a symbol of A of C to represent the centripetal acceleration. What does that mean? That means when the particles are here, the acceleration is this way, centripetal. When the particles here, the acceleration is that way. What about its velocity? And if we let this particle move counterclockwise, velocity is tangential. The magnitude is constant, but direction is tangential. So if we look at, let's say we choose anywhere right here, then in order to be centripetal, we need to point to the center of the circle. So the acceleration is centripetal, A of C. What about the velocity? It has to be tangential. So that's that. Now if we choose another position, then if we connect this as the radius, centripetal means that, and what is our velocity? That is this way, and that is v. So you can imagine when we come here, the velocity will be tangential and the acceleration is centripetal. So at any location, velocity changes its direction and acceleration also changes its direction. And this figure showed us that, as a matter of fact, during the circular motion, it could have two accelerations. One is called A of r, which is the acceleration around the radius direction. This actually is what we talk about, A of centripetal. The other is A of t. T means tangential. So it says the total acceleration is the radial acceleration, which is centripetal, plus a tangential acceleration. The tangential acceleration will be able to change the magnitude of v because v itself is tangential. Imagine that if AT is same direction as V, then V magnitude increase. If AT is opposite direction of V, then V's magnitude will decrease. However, the acceleration of C, which is centripetal, can only help the object to change its direction. It cannot change the magnitude of V. Look at this. For example, the particles here, it travels V. For delta t second, teeny little bit delta t second, because the centripetal acceleration is this way, then it will gain a teeny little bit of velocity towards this way. Then the combination of increase the delta V and V, the final V changes direction. Look, this is how it changes velocity to get turned around. So centripetal acceleration can only help the particle to turn around, change the direction of velocity, but tangential acceleration helps the particle change the magnitude of V. Now, let's figure out what is the magnitude of centripetal acceleration. We know that the particle's position vector OP equals to r of cosine omega t of I plus r of sine of omega t of j, as we actually had that before. If this is x-axis, this is the y-axis, a point particle P is r meters away from the origin, and this angle is omega times t, so the distance is the radius r. So therefore, if we talk about its x, which is right here, that will be r of cosine omega t. If we talk about y, which is right here, that will be r of sine omega t. So if we use unit vector I and j to help this, we have this much I, that much j. So if we want to know what is the velocity of this particle, since this is a position vector, this is actually just the position vector r. Remember, instantaneous v is the r dt. This is universally true for one-dimensional or two-dimensional, three-dimensional. We encountered this dx dt equal to v in chapter 2, dr dt equal to v for three-dimensional at the beginning of chapter 4. So let's differentiate this. When we differentiate this, because r is a constant, we need to differentiate cosine. Cosine of a variable will change to negative sign. And then we will differentiate omega t. Omega is constant, so omega comes out. So what happens is if we differentiate the first term, okay, we get negative and r omega sine omega t, and I still stays because this is a constant. When we differentiate sine, sine changes to cosine. So we have r of this omega also come out. So r omega cosine omega t of j. This is the velocity expression. The velocity is tangential, and the position is our radial direction. There are 90 degrees of difference. Believe it or not, in the future you're going to learn a vector, let's say r dot another vector, which in this case v. If r dot v, okay, the mathematical definition will be r's magnitude, the other one is v's magnitude times cosine of theta. So if r dot v comes out equal to 0, that means the angle theta between r and v is 90 degrees. In this case, it is because r is around the radius direction, v is tangential, so they're 90 degrees. So we will learn that in the future. Actually, when I dot I, that equals to 1, j dot j, that equals to 1, and I dot j equal to 0. So you can see that if we have this term, which is this one times that one, we get negative r squared of, so in our case will be, the first term will be negative r squared of omega and sine omega t cosine omega t. That's the first term. And because I dot I equal to 1. And then at j dot j term, we have r squared and omega and sine omega t and cosine omega t. J dot j equal to 1. So that is the result. Don't you see they add together equal to 0? This confirms that r is perpendicular to v, which means during the circular motion, velocity is tangential. Velocity is 90 degrees with respect to the radius. Okay. So if we continue this similar method, we can find acceleration. Acceleration instantaneous defined as dv of dt. So if we differential v, we'll get a. So this is the v expression. We're going to differentiate that. So we differential sine of omega t, and we change to cosine. Omega come out. So it's negative r omega squared. Sine change to cosine, so it's cosine omega t. I stays. And then cosine differentiate will be negative, and r still stays. And one of omega comes out one more time, so it's omega squared. And cosine change to sine, j. Now, I would like to do is that I'm going to pull this r omega squared out. And I'm going to pull this negative out. So what's left will be cosine of omega t of I plus sine of omega t of j. Well, actually, I should put this r back into here. So if I rewrite that, it will be negative. That is, okay. Well, let's keep this r outside for a little while. Now, first of all, I want you to take a look at direction. This r is called centrifugal because it's pointing away from the center of the circle. Look at the expression, that is r cosine omega ti plus r sine omega dj. So as a matter of fact, if I want to rewrite it, I have this r. Here is the magnitude. As a matter of fact, the cosine omega ti plus sine omega tj is the unit vector of r, which means it represents the radius direction. The magnitude is 1. How do we do that? For example, look at this. R naught if is cosine of omega t I plus sine of omega t of j. We define because I pull this r out. Isn't that true when you want to get magnitude? It's x squared plus y squared square root. Cosine squared plus sine squared square root is 1. So this r naught is a unit vector. R naught magnitude equal to 1. It represents a unit vector along the radius r direction. So r can be expressed as its magnitude times its direction. This is a unit vector. This is a unit vector along the r direction. Now let's come back here. Isn't that true again? This is a unit vector because we just defined cosine omega ti plus sine omega j. So if I rewrite this acceleration, that is a negative r omega squared of r naught unit vector. What does that mean? Right now our acceleration is a negative of the r direction. So r direction is centrifugal, negative r direction will point to the center of the circle, that's called centripetal. So the direction of acceleration is centripetal. And what is this? This is the magnitude of the acceleration. Because look, r equals to its magnitude times direction. So A equals its magnitude, direction is negative r0. That is centripetal. So therefore, our centripetal acceleration, the magnitude looks like equals to r omega squared. This is a very important conclusion. The magnitude of centripetal acceleration is radius times its angular velocity squared. It's r times omega squared. Well, we learned that the relationship between omega and v. Do we remember this v? Tangential velocity v equals to radius times omega. So therefore, if we want to replace this omega, that omega is v over r. So if we continues that r stays, omega will replace by v over r. Don't forget about square. We get that centripetal acceleration has another expression which is v squared divided by r, because when this r gets squared, one of r cancel with this one. So centripetal acceleration either can be expressed as v squared over r, tangential speed squared over radius, or it's r times omega. That is the radius times angular velocity.